get started. We're going to talk right now about oxymercuration, demercuration, and why are we looking at another type of synthesis for the hydration of basically an alkene. And that's because we want a Markovnikov orientation, just like when we did the acid and water. However, when we do the acid and water, we go through a carbocation, so rearrangements are common. If we actually do oxymercuration, demercuration, we get no rearrangements, but we do get the Markovnikov orientation. So it comes in two steps. Step one is you have mercuric acetate, and your solvent in this case will be water. And what happens is when you do step one, you form an organomercurial alcohol. Okay? Step two is you take your organomercurial alcohol and you reduce it with sodium borohydride, which essentially is a mild hydride. Okay? And when you do that, you actually reduce your mercury from a mercury 1 or mercury 2 state, mercury 1 state, down to mercury 0. Okay? You're going from mercury 2 state down to 0. And you form your sodium borohydride, but it's not borohydrate, now it's a hydroxide. It's 4, should be on the outside here. Okay? And you have 4 acetates. So let's go through and talk about your mechanism here. And I'll show you at the same time your Markovnikov orientation. Okay, so let's do this example. Let's suppose I take something like, what is that, my 2-methyl 2-butene. And I add in my mercuric acetate. Okay, so let's look at the mechanism on this. So before we start drawing my arrows, let me just tell you that this actually is an equilibrium. Looks like this. Here is my mercuric acetate. So that's a mercury 2. Okay? And this is actually an equilibrium with my cation and my acetate. Okay? And this, saw me designate it earlier, that's the abbreviation for an acetate. As you can see, with this being my positive charge, this acts as my electrophile. So when we talk about electrophilic addition, we have to add my electrophile. Now when we do this, just redraw it here. It's easier to see than having those arrows go all over the place. It's going to be ACO Hg plus, right? Acetate, or if you want, you just draw it more cleanly so you can see it's an acetate. Okay. So now my 2 electrons from my pi bond attack my mercury. Okay? But what happens is when these 2 electrons go into the mercury, it can actually come back and attack that cation. Okay? So, this is what happens. What you get differently so it's a little easier to see. So these electrons form this bond to the mercury, but then that comes back and forms a bond to this carbon. Okay, so you get this cation. All right. Now what's interesting now is, let me just talk about this cation before we continue. Doesn't this remind you, actually, because of the asymmetry here, in a sense, this is 1, 2, 3. This is a tertiary carbon. This is a secondary carbon. So if I distribute this positive charge, this can stabilize my positive charge a lot better than my secondary carbon can. Okay? So bear in mind, this is how we're getting our Markovnikov orientation. This is more stable. We always want the more stable intermediate. So, let's go on. Now, we've just added my mercuric acetate. What about the water? What about my solvent? So, as we continue with your mechanism, we have CH3 here. We had CH3 here. And we said, since this is tertiary, this is secondary, this stabilizes a positive charge much better. So, if this can stabilize my positive charge, then I can, when I distribute, this will have a larger positive charge. It can hold it. It's kind of like if you have a pocket and your friend doesn't, you could probably hold your friend's cell phone in your pocket along with your cell phone. While the other person, your friend, doesn't have to worry about where they're going to put their cell phone down when they have to do something. Now, why do I mention that? Now that we know that my tertiary carbon, when I distribute my positive charge, can stabilize my positive charge more, then where are the electrons on my oxygen going to go? They are going to go not to my secondary carbon, to my tertiary carbon. When you do that, what we've done is we've formed. That goes there. Keep pushing my electrons. Those electrons go onto the mercury. Okay, what you get is that mercurial, organomercurial alcohol, but not quite. It's a protonated alcohol. So our solvent comes in again. Takes off. My proton. And now I get my organomercurial alcohol. So that's our first step when we do the synthesis. Now, what happens to this? Okay, so let's take a look at my hydride. So before I do the mechanism, let's talk about sodium borohydride. Sodium borohydride is a reducing agent. Okay, it looks like this. Okay, and what happens is all my hydrogens are actually hydride. Okay, in other words. Now, why do I use sodium borohydride instead of sodium hydride? Having sodium hydride, just like this hydride is extremely strong. And in fact, it's almost too strong for what we want. So by having a complex to the boron, it still gives it the hydride characteristic, which is what we want. That's why it's still reducing. However, it allows us actually to use it in protonated solvents like water and alcohol. So it's a weaker reducing agent than just sodium hydride or lithium hydride, but it does act as a hydride. So when I show you the mechanism, I'm going to be drawing this, not because I want you to think about using lithium hydride because that's too strong, but I want you to be thinking about this because that's actually what we're interested in seeing what happens. So let me just go ahead and draw you. Okay, what I put in my hydride, my sodium borohydride, one of my hydroxides. So when we do this reduction with sodium borohydride, we're going to do it in a basic environment. Displaces the hydride. So okay, so that's what we're really thinking about. Like I say, it's not a raw hydride, but essentially what you're doing is you displace the hydride. The hydride then acts as a nucleophile, attacks my carbon. Okay, when that happens, let me just draw my acetate out so you can see what happens here. These two electrons come into this carbon. These two electrons go onto the mercury, and those two electrons go onto the acetate. So what I get is this. I'm going to draw it right here. That's how we reduce the mercury. And that's how we got one of our acetates. But notice I have 3 more hydrides that I can use in this compound. And that's why when I gave you the end result, you're going to see 4 acetates formed, because you can do this 4 times. You'll get 4 mercuries formed. you'll get 4 alcohols. Now, let me show you the overall reaction. The reason I want to show you the overall reaction is then it'll be very clear how this is your Markovnikov orientation. Okay, so let me go ahead and put it all together for you. Methyl butylene. Make that a nice carbon there. And if I do multi-steps, I put 1 mercuric acetate. And I'm going to use my solvent water. Okay. In step 2, I'm going to use sodium borohydride. And notice how we needed to use a hydroxide in order to displace it to get the hydride. So I'm going to put the hydroxide in there. When you do, your product will look like this. Okay, so that's your product. Now, if you're just thinking about my water, this being my electrophile, this being my nucleophile, okay, then where did my electrophile go? On the carbon that had the most hydrogens, right here. Okay, where did my nucleophile go? On the carbon that has the fewest hydrogen, right here. So this is the Markovnikov orientation. Now, why do we not have any? There's no stereo specificity. Okay, we have regiochemistry, but not stereospecificity. And that is because here we know we're going to be trans to the mercury. But when we do the reduction with my hydride being as small as it is, it won't only do the backside attack. It can scramble, and therefore you can get 2 different isomers here. You're not going to see that. This is not a stereocenter. But just so you know, that's something to remark on this one, on the oxymercuration, demercuration. Okay, so let's stop here, and we will then talk about what happens if you want an antimercuration.